Good morning, class. Today we start virtual memory, which is an extension of the memory management that we've been studying the past 2 days. Today we'll take a look at these three topics, and here are the chapter objectives. All right, first some background. So we've been saying that the entire program of a process needs to be in memory to execute, but when you think about it, only the instructions actually being executed need to be in memory. And for a large program, may be large parts of its program that never execute or rarely execute. So if we eliminate the restriction that the entire program be in memory, we can now allow programs that are larger than physical memory to run, so long as we have some mechanism for bringing in those portions of the program that are executing. So programs take less space, meaning we can increase the degree of multi-programming, i.e. more processes running. And finally, there's less I/O to bring a program into memory, meaning that we can begin executing it more quickly, reducing response time. So this is what's known as virtual memory, and as you can see here, it's a separation of the logical memory space, which previously could be no larger than the physical memory space, from physical memory space. So now the logical address space, or we'll call it the virtual address space, can be as large as needed. And if managed well, that gives us a number of advantages, some of which we talked about. Here's one that we haven't mentioned yet, address space sharing. All right, continuing the background, this first bullet, there's nothing particularly new here with respect to what we've been discussing and what we had discussed in memory management with respect to logical address space. With a logical address space that can start at 0. Again, physical memory is organized into frames, and the MMU has to map logical to physical addresses. What is new is that virtual memory uses demand paging, which means pages are brought into memory only when they're needed, and an additional requirement is a mechanism for recognizing when a page is in memory and when it's in backing store on disk. So here's a diagram. The virtual address space of a process shown against physical memory, and with the implication that the virtual memory can be larger than physical memory. The page tables, and what this illustrates is that some of the pages are in physical memory and some of the pages are on the backing store or disk. So when a request is made for one of these pages that's on disk, the page has to be brought into a frame, and potentially some other frame be stored back to the backing store. So there are a couple of wins here. Let's take a look at the traditional address space with its 4 segments: code, static data, heap for dynamic data, and the execution stack, and they're usually allocated this way. If you're not using virtual memory, then all of this unallocated storage or unused storage has to be allocated, and frames found for it. With virtual memory, only the in-use portions are mapped into memory, and as the stack grows, then frames are allocated, or as a heap grows, frames are allocated. So this reduces a process's memory footprint and allows it to begin executing more quickly because we won't have to allocate the space, so there's less overhead. In addition, this puts less pressure on the, the the compiler and linker because we can create as large a virtual address space as we need and don't have to worry about wasting space. So we don't have to allocate more space, or we don't have to think about what the maximum size of the address space needs to be. We can just allocate, and that also helps with dynamic libraries. With that virtual memory, there's going to be a certain amount of pressure into only allocating enough storage to fit a dynamic library into the address space, and then if that over time, if that dynamic library grows in size, then it may no longer fit into that space. With virtual memory, we can just create as large a virtual memory address space as we like, and not have to worry that it's going to waste physical memory. So here's a figure illustrating that idea, and again, I want to emphasize that with virtual memory, we don't have to predict the size of this shared library code. We can just allocate large virtual address space and worry about things later. If we're not using virtual memory and we don't want to waste physical memory, then there's going to be a certain amount of pressure on us to not over allocate or not over allocate the amount of physical memory given towards shared libraries. So demand paging is the idea that a process's pages are only brought into memory when they are actually demanded or needed. So this this improves the process's startup time and reduces its memory footprint. As noted here, it's similar to swapping, except with the swapping that we talked about in the last chapter, swapping was at the level of the entire process's address space. Now we're performing swapping at the page level, and what needs to happen within the page table or the MMU stage of address translation is recognizing three states of a page: in memory, on the backing store, or it being completely invalid, which will result in a trap, which will cause a process to be terminated. If a page is recognized as not being in memory, as being on the backing store, then a page fault trap is generated, and that will cause the page to be brought into memory, as we'll see shortly. All right, I've already talked about many of these ideas, so I'll just pause here momentarily so you can scan the slide. So now we have an additional use for the valid bit in a page table entry, where the valid bit now indicates that the page is in memory, and the valid bit is not set, meaning invalid. That implies that the page is either on the backing store or not within the process's address space, which would generate an invalid reference trap. So here's an example in which the process's virtual address space is 8 pages, and all of those pages are on the backing store, but only 3 of the pages are in physical memory. So page A is in, or yeah, page A here is in physical memory. So that's page index 0. So a reference to that page goes to index 0 in the page table, and you can see that it's in frame 4. This page labeled B is not in physical memory, and you can see that its page table entry, the valid bit is not set. So when a page is not in memory and a reference is made to it, we incur what's known as a page fault. So the operating system determines whether the page fault is because of an invalid reference or simply because the page isn't in memory. And assuming that it's the latter, then the operating system has to find a free frame. If there, it may maintain a list of free frames in order to, well, of course it maintains a list of free frames, but if that list is empty, then we have to find a victim page, as it's known, to page out in order to free up a frame. Then the page has to be swapped into the frame that was located, the page table updated, and then the instruction that caused the page fault has to be restarted. Again, here's an illustration. So an instruction, a load instruction is executed. That results in a page table, or the MMU performing a page table lookup, finding the valid bit not set. That causes a trap to be generated. The operating system determines that the requested page is on the backing store. That's going to ultimately cause a context switch. So an IO is set up to transfer the page from memory into a free frame. That's at this point that IO is set up, and then at that point a context switch is performed. Meanwhile, the IO device brings the page into memory, eventually generating an interrupt. The operating system determines that that interrupt is due to the completion of the IO. The operating system updates the page table, and eventually when this process is once again selected to run, that instruction is restarted. The extreme case, we don't bring in any of the process's pages, so the only way it gets running is by generating some number of page faults. Fortunately, due to the way programs execute, there's this notion of locality of reference, which there are a couple of aspects of that that we'll talk about in more detail later. But typically, if one instruction executes, those near it execute, and those instructions are likely to be in the same page, resulting in those subsequent instructions not generating page faults, or in the case of loops, a particular instruction is executed over and over again. And as we've already talked about, the hardware that we need to support demand paging are swap space, the ability to restart instructions, and a page table with a valid invalid bit. Instruction restart can be kind of tricky, particularly with respect to CISC architectures, and that's all I really want to say about that. This is more an architectural issue than an operating systems issue. So all this sounds great so far, but let's not forget about the performance hit that demand paging can cause. So remember that memory access takes a few hundred nanoseconds, whereas going to a mechanical disk drive and access there can take milliseconds. So we're talking about a difference of 6 orders of magnitude or so. So we want the page fault rate to be extremely low. And one more time, here are the worst case, not worst, but worst case steps in demand paging. So an operating system trap, save process state to prepare for the context switch, find the page on the disk, start the read from the disk, perform a context switch, receive the interrupt from the disk and process that interrupt, perform the interrupt response, correct the page table, wait for that process to be scheduled once more, and then perform the context switch and resume the instruction that had originally caused the page fault. So the 3 major steps there are servicing the interrupt and performing a context switch. In a relative sense, compared to the disk I/O, that's short, as is performing the context switch to restart the process. What takes the most time is reading the page in from disk. So we have this notion of a page fault rate, which is a number p, a real number p between 0 and 1. If the page fault rate is 0, that means that we are incurring no page faults whatsoever. If the page fault rate is 1, then that means that every single memory reference is a fault. Right, and we can encapsulate that into an effective access time equation, which is 1 minus p is the probability of a memory reference not generating a page fault. So the weighted average, which gives us the effective access time, is 1 minus p times the time for memory access plus p, the page fault rate, times the amount of time necessary for servicing a page fault, right? And that's going to include potentially swapping a victim page out and bringing the desired page in. So for a specific example, let's assume a memory access time of 200 milliseconds, 8 milliseconds to service a page fault. And here is the equation. And if one access out of 1,000 causes a page fault, then the effective access time is 8.2 microseconds, which compared to 200 nanoseconds is an excessive slowdown. So if we want a performance degradation of less than 10%, we can see that the page fault rate needs to be such that we only incur 1 page fault every 400,000 memory accesses, which seems kind of mind-boggling, but is what is seen in practice, given a sufficient amount of physical memory. You may have experienced this yourself with older PCs, but often the easiest way of increasing the speed of a PC is to simply not plug in a faster CPU, but to add memory, because of excessive page faults. There are a few optimizations that we can make. Rather than allocating a swap file within the file system, we can use a swap partition, and that eliminates file system overhead, speeding up swapping. We can then copy the entire process image to that swap space at load time. Of course, that's going to incur some overhead until we have that entire image in swap space. Another thing we can recognize is that some of the pages don't need to be swapped out if they're, for instance, code pages, because code pages don't change. We can simply read them from the file system or from swap space. And similarly, pages that are created dynamically, such as the data area, once that's on the backings door, those pages don't need to be swapped out if they haven't changed. So that implies, as we'll see later, that the page table entries contain a bit to indicate whether a page has been modified or not. Copy on write is a technique used to speed up forking operations. So remember, when a child process is forked from the parent, it's an exact copy of the parent, which the optimization that we can use is to allow the parent and the child to share address space until one or the other modifies a page, and at that point, upon that write, then a copy of the page is made, so that we can maintain the notion that the address spaces of the parent and the child are unique. So here's an illustration. Let's say that process 1 forks process 2. So initially they're sharing all of their physical memory in these 3 pages. Then process 1 performs a write into page C, and at that point a copy is made of page C, so that process 2 still sees the original data. And as I said before, this maintains the separation of the process address spaces. So this is a teaser for our next screencast. What do you do if there's no free frame? And that raises questions of how many frames to allocate to a process, and well, ultimately, what do you do if there's not a free frame?